I'm here with Rick Bacon now, and Rick, how you doing?
Great to see you again.
So we've been interviewing a number of companies and presenters about, treating difficult to treat contaminants. What are some of the things you've learned, from listening to some of these conversations with, some of them are your competitors, some of them are engineers, that we had a mixed bag of folks. What do you think?
Well, I think obviously PFAS has sort of dominated the conference, whether it's the percentage of papers given on PFAS, or the number of exhibitors here where the PFAS something is on their poster. The other part of that is that I think the broad range of approaches, I find it very difficult on the consumer end to decide between an extraction technology of one sort or another, or an absorption technology, or a destruction technology. So I think that if I was on I need to treat for PFAS, I find it very, very confusing. I think the other thing that's left sort of unaddressed is that there's a lot of what we call extraction, so capture technology, which is great, but then what do you do with what you've captured? And I think it's an unwritten concern, but it's out there. So if you think about, I'm going to spend $1 million on capturing it, the capital, $4 million a year on the sort of OPEX, it's like 20 million on the back end. And I think that's where there are still a lot of unanswered questions.
Yeah, it's interesting because almost everything is a multi-step process. You pull it out, you dry it up, you send it someplace else, you destroy it, you landfill what's left over. That's, I think, part of what the customer maybe doesn't understand is just treating for it isn't the end of it. And so some of the solution providers we've talked to are end-to-end, and some of them are just one of those steps. And so that's like another interesting piece about, maybe what do you think is the best way to go about, entering this business or being in this business? Do you think it should be a full-on service provider? Do you think you should have one piece of the puzzle and then partner with somebody who does, say, the destruction side? What do you think about that?
If you look at all those technologies, they're quite different. And I think it's very difficult for one company to have all of that. I think there's some very good players in call it extraction capture technology, very different. And that has different implications for then how you destroy and whether it's even destroyable. And I think that's going to get uncovered over the next couple of years. Our position is very much on the destruction end of things. And so our focus is very much who's producing concentrated PFAS, okay, and can we help them solve the problem? Because some people would say, oh, it's just another can. We've got it out, someone's going to kick it down the road, don't worry about it. And my view is we've got to be able to offer a proper end-to-end, I won't call it a solution, but system that delivers what's required, which is to eliminate PFAS from the water cycle. If you just put them on the top of the mountain, having captured them, and they flow down into leachate and then into groundwater, you just move the can around a bit, right?
That's right, just dilute it a little bit more. So we've been talking about PFAS, but there's a number of other chemical compounds and antibiotic resistant bacteria, pharmaceutical compounds, microplastics. Is AMS involved in all of those kinds of recalcitrant contaminants, or just are you focused on PFAS?
So one of the joys of this technology that we've developed is that it is multi-application. So we can generate ferrate on site, and it's a chemical that is the most powerful oxidant around, more powerful than ozone. So you immediately think, well, what does ozone do? We could replace ozone. Ozone, very, very costly capital, very costly to operate, and not very nice to operate. So there's sort of replacement there. But there's, and you know this because you wrote the papers, there are multiple papers done on the applications of ferret, right? And they all sort of conclude with, it would be nice if you could produce this on an industrial scale, then we could do something with it. And what we've been able to do is sort of take it out of the lab and produce ferret on an industrial scale. Its biggest weakness is that it's got a 5-minute lifetime.
Right.
So you can't make it in a factory like ferric chloride and ship it. So you have to make it on site, and when you make it on site, you can then attack this broad range. I don't know how many papers you covered, but I mean numerous applications, whether it's endocrine disruptors, PFAS, general organics removal, azoles in semiconductors. So we've sort of got this toolbox, and the question is which do we go after first? But it's a nice place to be, and we've just got to develop the applications.
And ferrite is an iron-based compound, right?
Right. So ferrite is produced the way we do it electrolytically. So we're dissolving steel plates electrolytically. It is not electrochemical oxidation, which has serious limitations. We're producing ferrite in caustic soda. Those are the two consumables, and producing this very concentrated reagent, which has these amazing oxidizing powers. The joy of it is when it gets consumed, it gets converted to ferric hydroxide, which is a coagulant. So you're actually getting two shots for one. It's a fascinating chemical, but I think it is anyway.
Yeah, well, and it's interesting because most oxidants cause, some byproduct that's bad. This one's interesting. It causes actually a positive byproduct,
Exactly,
which
yeah,
is that never happens.
That's good.
There are so many different technologies out there that purport to be able to treat ferrite in some way, shape, or form. What do you think of kind of the overall vetting process for these technologies? I ran a research center, and we were able to treat or test, say, microfiltration systems on the same water. So we had, a side-by-side comparison, apples to apples, and we could tell, okay, this one worked this well, this one worked that well. I don't know if there's any place that's available to vet these kinds of technologies.
It's really, from our position, it's really difficult. You can go one route, which is sort of look for public funding. That takes an age. Just going through the RFP process, you've got to tie in with academics. By the time you put all that together, it's 4 or 5 years down the road. People in our position don't have 4 or 5 years. We want it out there. So what we've done is sort of agnostic to that. We've found the early adopters, and we've had to seek them out, who are willing to try it and do a sort of proper protocol and all that stuff. But it's really hard unless you've been it's like a catch-22. Unless you've been in the industry long enough that people will trust you to let you go and play on their site, you're never going to play. And if you haven't played, how do you build trust? So I think that there are instances like the water tower in Georgia, which have got a broad set of facilities where people like us can go and play. It's managed rigorously. It can even be assessed independently. We can drop in our technology, have an engineering group or whoever do the validation, and then that's published and it sort of stands the test. But getting that independent validation, which is what we've had to do numerous times, is very costly, and it slows down adoption.
Right. So another piece of the puzzle is the monitoring side. Whenever you're treating anything, you have to know how much is there to begin with.
Yeah.
Know how much is there at the end, and that tells you, one, if your equipment's working, if you're meeting the discharge requirements, whatever, and ultimately tells you if the technical efficacy and the value proposition of your product. So how do you do the monitoring side?
So that's actually how we got into treatment. So we built this portfolio of advanced water quality analyzers. And in fact, we were being used by engineers for precisely that purpose in California, who wanted to know how effective their chrome treatment system was. And it was through that, it was like we became insider traders. We could see the limitations of RCF, reduction calculation filtration, reverse osmosis, ion exchange. But this is crazy. This data shows that they're falling over every 5 minutes, or they have to backwash every 2 minutes, and that's not sustainable. And in fact, they were so costly that the state withdrew the regulation until later on, when we turned up and sort of moved things along. But being able to monitor the influent, and it's never stable, and then monitor the effluent and know that it is stable and it's well below the limit, is absolutely critical. And we've designed our treatment systems to incorporate that, because you need to know that you don't want to be so efficient that you're driving up your energy costs and greenhouse gas emissions. You want to know that you're achieving the goal without over-treating, but not under-treating.
Right.
And at the same time, your influent is all over the place. And so real-time monitoring integrated can help that whole process.
So let's talk about PFAS again. Is the U.S. market kind of driving things? Do other countries have PFAS regulations?
So Europe's sort of getting rapid. So yeah, definitely US. And I've talked to some people here who think it's sort of gone completely over the top. I mean, I think there are definitely sites where the levels of PFAS are problematic. But it's sort of become such a widespread issue. We've got regulation for drinking water, but actually I think the real problem is wastewater, because it's wastewater that's ending up in drinking water. So I really do not understand why there aren't regulations around wastewater. In Europe, we were there a couple of weeks ago, they talk about TIFA. Have you heard of TIFA?
No.
Well, it's another short chain, and they're actually more worried about TIFA than they are about PFAS. I mean, it's a subset, really, I guess. But so yeah, I think there is a general concern, but they haven't gone anywhere near as far as the US.
So what's next for AMS? What's the next big challenge?
Find some money, spend it, investigate, develop applications. You know, it's a sort of it's like think about it as a chair, right? You've got to have the clients, the engineers, the product, and the money, and you've got to keep all of those things sort of moving forward. But we're now winning our first major treatment contracts, and that's going to change our profile in terms of growth and presence in this industry. So it's a very, very exciting time for us.
Great. Well, thanks so much for chatting, and this is a perfect end to a very successful conference, and thanks a lot, man.
Thanks for making it successful for us.
All right.